Hello, everyone. So first, let me introduce myself. I'm Imam Rani Alawi, and I have been working in Transvalor for 1 year by now, after my internship in Aubert Duval. And today, the topic of my presentation is the procedure used to improve the identification of material parameters for recrystallization in DGMU. During my internship, I have worked on microstructural evolutions of different nickel-based alloys during hot forging conditions and heat treatments. It is clear that DGME productions are helpful to understand and optimize parts obtained from industrial processes. However, identification procedure for recrystallization is not trivial and necessitates an important amount of work. This was precisely the topic of my work, and I will give you an overview about the actual procedure and the potential approaches to improve it. So my presentation is divided into 3 main sections. The first part is dedicated to the experimental work needed to study microstructure evolution for each physical phenomenon: grain growth, dynamic recrystallization, and post-dynamic recrystallization. The second part is dedicated to the identification procedure of material parameters for DGMU and for each mechanism. Finally, the third part is concentrated on the potential optimization and accelerations of identification procedure using optimization algorithms and neural network. So the first stage in studying microstructural evolution is the experimental work. This step is primordial to better understand the behavior of any material. And first of all, in order to understand the mechanisms of grain growth, microstructure evolutions need to be analyzed through several interrupted heat treatments and microscopic observation. As the table shows here, a total of 12 tests, for example, are needed to cover the whole domain. And also, the tests are quite simple because only optical microscopy is needed to study the grain evolution. But be careful, one thing that we need to check before the beginning of the test, it is the initial state. The polycrystal must be fully recrystallized and free of any stacked energy. The second step in the experimental work is realizing dynamic recrystallization tests. So this table represents the corresponding design of experiments. For each thermomechanical condition, 2 inputs are needed. First of all, we need a flow stress curve like this one. And secondly, we need several interrupted tests to be performed with microstructural evolutions to characterize the evolution of recrystallization at different strain levels. So as you can see, there is a lot of experimental work needed here. In total, we have 60 tests to be done, in addition to microscopic observations. However, if we are short in time, we can only perform the test in green, and they will be and it will be at least needed to study the influence of temperature and strain rate on recrystallization. Finally, be aware of the quenching time's influence on the microstructure, which may evolve significantly in few seconds. Next, here is an example of the experimental data that we can obtain from dynamic recrystallization tests. First of all, we have a set of flow stress curves for different temperatures and strain rates, then some microscopic pictures. For easy cases like this one, only optical microscopy is needed, since we can differentiate the recrystallized grains from non-recrystallized grain only by their size. However, in more complicated cases, EBSD, with example here, the ghost maps, can help us a lot because it permits us to see clearly the less hardened grains in blue that are corresponding to the recrystallized fraction in general. Finally, microstructural evolutions are also studied in post-dynamic domain, with different holding times at high temperature before cooling. So for example, here the ghost maps show the evolution of recrystallized fraction after 2 seconds, 10 seconds, and 30 seconds after the end of deformation. This brings me to the end of my first point. Once the experimental work is done, we move on to material parameters identification. This part, of course, is dedicated to DGMU parameters. So I will start by presenting the current identification procedure used in DGMU to simulate each physical phenomenon separately. Firstly, the grain growth mechanisms are linked to the grain boundary mobility that depends only on temperature with two constant parameters that are M0 and QM. Secondly, we have dynamic recrystallization, which is divided into several physical mechanisms. Firstly, hardening that would be presented by parameter Q1 and recovery by the parameter Q2. Both of them, as you can see, they vary according to temperature and strain rate conditions. Next, we will have nucleations and the grain growth parameters during deformation that characterize the evolution of the recrystallized fraction. And as you can see here, for simplicity reasons, we consider KG depends only on strain rate and delta depends only on temperature. Finally, one last parameter, delta S, that acts on recrystallized grain growth velocity after deformation and depends only on temperature. So I will start off by presenting the identification of the grain growth following an Arrhenius law that depends only on temperature with two constant parameters, the pre-expansion parameter M0 and the activation energy parameter Q. First, we search the mobility value for each temperature. We start by running a first DGMU simulation with a trial mobility that can be deduced from Burke and Turnbull model. And we obtain the green curve that we see here. And after that, we compare the results of this simulation to the experiments, and we can deduce the real mobility. And if we run a simulation with this new mobility in DGMU, we would obtain the red curve, as you can see here, that permit to fit better the experimental points. Then, once we have obtained the mobility for each temperature, we identify the parameter of the Arrhenius law, M0 and QM, that describes the evolution of mobility at each function of temperature. In short, it is a simple identification procedure with no difficulties. Now I will move on to the identification procedure of the following parameters: the hardening parameter Q1 and the recovery parameter Q2 of Johnson-Lazzarabi-Jonas law. As you can see, they describe the evolution of dislocation density, which is linked to flow stress by Taylor equation. So previously, we only tried to fit this the stress strain curve that is to identify the parameters Q1 and Q2, and we used to fit just this curve in the hardening recovery domain before the start of recrystallization here. However, we noticed that these two parameters affect directly two important values of the model: the critical dislocation density, or the critical strain, and also the nuclei size. In other words, this identified Q1 and Q2 parameters will affect the start of recrystallization and also the grain, the recrystallized grain radius or size. Our priority here, as I said, is to fit the microstructural evolution. That's why we now we identify Q1 and Q2 based on the critical and the nuclei size values and not based on the flow curves. This table next is presents a set of parameter values extracts from stress strain curves and also microgravity observations that we need for the identification of key 1 and key 2. Also, in this stage, there is no need to run any DGMU simulation. All the identification work can be done in Excel. We have 3 main steps. First, we start by smoothing all the inputs that we have obtained from the stress curve. And the objective is to consolidate the experimental data using simple laws of fitting. Then raw values of key 1 and key 2 for each thermomechanical condition can be computed. And finally, the key 1 and key 2 values are smoothed to better interpolate and extrapolate the values on the whole domain of the temperature and strain rate. This procedure is quite simple. This procedure is quite simple, but necessitates some manual curve fitting work. Here, I will show you, for instance, the smoothed curves used in the identification of the superalloy Inconel 718. We start by the fitting curves that pass by most of the experimental input points. As you can see, their evolution seems to be logical. Then we smooth the raw values of key 1 and key 2. That shows the quite good results also. So at this point of the procedure, we have parameters that ensures 3 things. First of all, a reasonable description of the flow curve. Second, the right critical strain, which ensure a correct start of recrystallization. And finally, the correct size of the recrystallized grains. Next step is the identification of the parameters describing the evolution of the recrystallized grains. Nucleation rates, Kg, which will affect the number of nuclei appearing during recrystallization, and parameter delta, which will affect the velocity at which nuclei will grow during deformation. This will be done in DGMU by inverse analysis. And at this point, a large amount of DGMU simulation will be needed because inverse analysis is not only done by one single simulation, but on the whole design of experiments. So this procedure is longer than the previous ones because of the computation time that takes about 1 week for the whole procedure. In general, we start the identification with those advised set of parameters that we can see here in this table. Then, using visual comparison, we can adjust the 2 parameters. In general, as you can see in this example, after we identified the parameters Kg and delta, we have obtained a good overall good fit of experimental results with a smooth, monotonous, and logical evolution for each parameter. Finally, the last parameter to be identified is delta S, that represents the velocity at which nuclei will grow after deformation. So to find this parameter, we search at each condition the value of delta S using inverse analysis with DGMU simulation. We first start by running a simulation in DGMU with the same value as delta. Then we refine it using visual comparison of nuclei size between experimental and simulation micrography. In this example, results obtained with simulation are in good agreement with the experiment. We can see clearly the growth of the recrystallized grains in blue after a few seconds of holding time after the end of deformation. So in conclusion, this parameter allowed us to fit the microstructural evolutions in post-dynamic. This leads me to the final point. As you remember, we are concerned about the time dedicated to the identification of DGMU parameters. The actual identification procedure takes a large amount of time because of fitting work with Excel and also because of the inverse analysis with DigiMu. That's why we looked at optimization algorithms and neural network approaches to accelerate it. As you may notice, a big part of the hardening recovery identification work is done manually. All the fitting work of the experimental inputs, also the fitting of hardening recovery parameters Key1 and Key2. It takes approximately a few hours to be done, and automating those fits could allow us to accelerate the procedure and make it more reproducible. The work have been done on Python using genetic curve fitting optimization algorithms, and the results are in general satisfying. As you can see here, inputs are very easily fitted and Key1 and Key2 directly computed. Also, their evolutions are easily deduced. Moreover, you can create instantly the corresponding material file for DigiMu. However, you may pay attention to the potential errors in the experimental inputs because one aberrant point can distort the whole model and corrupt identified parameters as well. The inverse analysis is needed to identify delta and Kg and involves also very similar simulations. A lot of dynamic recrystallization simulation on compression tests at constant temperature and strain rates for different material and process parameters. So obtaining some simplified results to characterize the evolution of the recrystallized fraction and also the mean grain size could be sufficient for this identification. We have tried to run two neural network models to predict the strain at 50% of recrystallized fraction and also the radius of grain at 50% of recrystallized fraction. So the first step was creating a database from DigiMu simulations, and we used 2 to 3 to 5 values per parameters, which leads to 1,000 simulation that takes about 1 hour on one curve for each one in DigiMu. Here, I will present you the results that we obtained by the neural network model using one layer with 5 neurons to predict the values of strain at 50% of recrystallized fraction. So the graph here shows a comparison between the predicted values and experimental values. As you can see, interesting results were obtained. They are promising for most of the experimental points, even though we can see for a few of them, there is a big gap in comparison between the predicted and the experimental ones. Same goes for the prediction of the grain size at 50% recrystallized fraction, where a neural network model of one layer and 5 neurons was used. It shows clearly that the results are encouraging, but not perfect though. The study has encouraged us to go into investigating in neural network modeling to optimize our procedure. However, we have to admit that for now, the results still not accurate enough to replace DigiMu simulations. So in the future, we will work on these subjects with some specialists in this field to try to improve them. In conclusion, an overview of the identification procedure for each physical phenomenon has been presented. The experimental work is needed for better understanding of material microstructural evolutions, and diverse type of materials has been successfully identified and tested, such as superalloys, nickel-based, austenitic steels, and also the identification has shows relevant results for both of them. We also presented for you some approaches to optimize even more this procedure, but it is still at the moment into progress. Finally, do not hesitate to start an identification procedure with us. and feel free to contact Transvaal support at any step of this process. And thank you for your attention.